Hi, everyone. How are you doing? All right. Okay, so today we're going to talk about representations a bit more, especially of U1 and SU2. And then we'll start talking about the simplest quantum system, a particle on a circle. Okay, so last time I started introducing the basic ideas of representations. So the basic idea is that you have a group and we think of the group as a group of symmetries of something. So we have a group acting on a set, a group action, but there's a special type of group action, which is when it's acting on a linear space, on a vector space. And so if the group elements are being, so recall a representation of the group G on a vector space V is a map pi into the general linear group of V, such that pi G1, G2, the product of group elements acts by the product of matrices. Okay, so I just want to give another example of this just to really make sure that there's no confusion. So an example of this, you can construct a lot of these by considering permutation groups acting on finite sets. So for example, if X is a finite set, right, then of cardinality 3, let's say, then we know that S3, the symmetric group of all permutations of 3 elements, acts on this set. So for example, this is exactly how we usually write elements of the symmetric group. For example, or if I write it like this, 1, 3, 2, this is just cycle notation that says that 1 is sent to 3, 3 is sent to 2, and 2 is sent to 1. So we have an obvious action. So we have a group action, S3, into the bijections of X. Right? Or you could think of it equivalently as a map from the group across the set to the set, such that row of G1, G2 is row of G1. Yeah, I think you know what an action of a group on a set is. So this is your typical example. Okay, so this is not a linear action. It's just the action of a group on a set. But we can make it into a linear action by making the set into a linear space. How do we do that? Well, we can take the vector space generated by the elements of X. So an equivalent way of saying it, it's a slightly different, but well, actually, we might as well do it that way. So let's say that we take, let's say V. So let V be the complex vector space generated by these elements 1, 2, 3. I.e., what I'll do is I'll introduce a basis element, one for each of the elements of the set. So we'll use E1, E2, E3 as basis, and then V is just any complex number times E1 plus any complex number times E2 plus any complex number times E3. And we have a complex vector space of dimension 3. Okay, and because because you know how every group element acts on this set, you know how it acts on the basis. And if you know how a linear transformation acts on a basis, then that's all you need to know. So that defines a representation. So we obtain a representation of S3, on V, just by defining that that each element will act on the basis element exactly by taking it to the basis element that the permutation that the permutation does to the label. Okay, so you could think that the basis elements are labeled by a certain index set, and if we have a group acting on that index set, then it becomes a linear action on the vector space. So just to give an example, let's say that we want to know what is the matrix corresponding to the permutation 1, 2. Well, what does it do to E1? It sends it to E2. What does it do to E2? It sends it to E1. And what does it do to E3? It leaves it alone. So this is the matrix in the basis provided for this representation. Or if I want to do, let's say, 1, 3, 2, 1, 3, 2, that permutation now will become a matrix. All the permutations will become matrices, 3 by 3 matrices. Sorry, 3 goes, 2 goes to 1, 0, 1, 0. Okay, so every matrix, every group element has been now converted into a matrix, which is acting on this vector space, and we've got a representation. So I hope it's clear that the fact that this action is satisfies the action law. So in other words, the fact that if we compose two group elements and then act by that composition, it's the same thing as acting successively by the individual elements, right? Because of the fact that holds that it's really a group action at the level of sets, that will be inherited by the matrices. So we can be guaranteed that if we multiply the matrices, right, that will correspond to the composition of the group elements. Just because that's exactly how they act on the basis. And so if a composition of operators behaves a certain way on a basis, it behaves that way on the whole vector space. So there's no surprise here that we get group representations. Okay, now notice maybe it's useful to notice the fact that so is this okay so far? So this is just a really simple representation of a finite group of dimension 3. Any questions?
So far, so good. Seen this in abstract algebra.
Okay, all right. So, so then notice that. So in the abstract algebra, did you talk about reducibility of representations, irreducibles, and classifications?
Didn't quite get that far. No.
Okay, this is in which class? I'm just curious.
For like 347 and 1100.
Oh, I see.
Yeah.
Okay. So notice the following. Well, okay. Let me just draw a picture of this. So we've got a 3-dimensional space. Never mind that it's complex, and we've got our 3 basis elements. Which are special elements, which you could think of as being an embedding of the finite set into this vector space. Does this remind you of anything? It should remind you of the way that the switches are related to the 2-dimensional quantum space, right? So the classical states, they are kind of like the basis of the vector space, okay? And this group representation is acting on the classical states. So it's almost like the Z mod 2 group that we all use when we turn on and off the light switch. Okay, we use a Z mod 2 action on the light switch, and that becomes promoted to a Z mod 2 action on the vector space generated by the light switch states. And so that's why I picked this example. The finite set is analogous. So the finite set X is analogous to the classical phase space. And then this vector space generated by X, which I could call C of X. This is the quantum mechanical phase space. And what we see is that the same group that we identified as acting on the classical space, it lifts to an action of the group on the quantum space, but the action is linear now, and it's by matrices. And okay, and I just want to point out another thing, which is, let's say if I look at the transformation, which just rotates these, so the cyclic transformation 1, 2, 3. Oh, sorry, have I been switching between 0?
No, this was the first time you wrote it as 0.
Oh. 1, 2, 3. So this thing is just rotating the 3. Okay, I just picked one element just to take a look at it, and I notice very clearly that there is a special subspace, namely the 1, 1, 1, the space generated by 1, 1, 1, okay, which is invariant under the action of this element. It's sent to itself because this element is really rotating, and that's the axis of rotation. But actually, you can see very easily that this vector is sent to itself by all group elements, and any permutation, right, is just if you permute 1, 1, 1, however you want, you're always going to get 1, 1, 1. So this is a one-dimensional subspace. Excuse me. So we get a one-dimensional subspace, which is the span of the vector 1, 1, 1, which is invariant under S3, under this group. And okay, and well, okay, and then there's another subspace. Okay, which let me try to draw it. If I draw the triangle like this, and I just extend that to a plane, there's going to be a plane P, which is a two-dimensional subspace P. Sorry, what I mean, sorry, I don't mean that it's the plane through those 3 points. I mean, it's parallel to those 3 points. So this is a plane which is intersecting the origin and which is orthogonal to the green line. So this is the set of, let's say, A E1 plus B E2 plus C E3, such that, let's say, A plus B plus C equals 0. And if the sum of of these three, if A, B, C, if the sum A plus B plus C equals 0, right? And if we permute these things, if you permute A, B, C to B, A, C, C, B, A, whatever, the sum is still going to be 0. And so it's also clear that this subspace is sent to itself by the action of the group. So the conclusion is that this vector space is a decomposition, kind of decomposes into a trivial one-dimensional representation. This one-dimensional representation is called trivial because the group elements are all acting by the identity, one-by-one identity matrix on this subspace. They're doing nothing. They're not even multiplying it by a number. They're just acting by the identity. I mean, they're multiplying it by 1. Whereas this one is a two-dimensional representation. And this this is a two-dimensional non-trivial it's a representation. And both L and P are irreducible. You can see that by just seeing that if you take a non-trivial group element and you look at its action on P, on the plane, you can see that it like, for example, this one, 1, 2, 3, you can see that it rotates and it doesn't have any eigenspaces. So there's no way that group element is going to preserve any subspace at all, any proper subspace, except for 0. So we basically get a splitting of the representation into two parts, which can't be reduced further. Right. Is this okay so far?
Sorry, you said it had no eigenspaces, but are we working over the reals or the complex here?
Well, I'm working over the complex numbers, okay, and this rotation, if you pick the 1, 2, 3 rotation, let's say, then it will have an eigenspace, but these eigenspaces for the different elements of the groups, are all different. So what you're looking for is a subspace that will be sent to itself by all of the group elements. You could just write down any vector at all. Let's say 1, 3, let's say you put 1, 0, -1. And so this is an element inside P, right? And if I do the 1, 2, 3 rotation to it, this will be sent by 1, 2, 3 to let's say -1, 1, 0. And right away, what you can see is that you have produced a basis for that two-dimensional subspace.
Yeah, that makes sense.
that means that right away you are not going to find a one-dimensional subspace preserved by this group. Okay, now I want to change the interpretation of this a little bit. I want to think about, see what I did here was I took linear combinations of my states. Okay, so a similar way of thinking, which is it's really the same thing. I'm going to think of the vector space. You could also think of it as C to the X, which are all maps from X to C. In other words, I'm assigning a number to every point in a complex number to every point in the set, and it's no different. Obviously, the value of the number on E1 is going to be the coefficient in front of E1. So it's the same way of thinking of it. So you could think, for example, so the interpretation you might have is that an element in this vector space, you could think of it as a function on E1, E2, and E3. And so you could think of it as a wave function. It's a complex valued function on the set of points. And you could think of how this group is acting, and here's the value of the function on the 3 points, A, B, and C. And then as you move those points, you could instead think of how this group is acting on the functions on those points. This is a typical way of thinking in quantum mechanics, that you might look at a vector space of functions on your different classical states. The last thing I want to say, finally, in this example, for this example, there's an easy way to define an inner product, a Hermitian inner product. Namely, you just inherit it from the complex numbers themselves. So, so let's say F. Let's say F and G are maps from X to C. Then we'll define the inner product of F and G to be the value of F at P, complex conjugate, multiplied by the value of G at P, and then we just take a sum over all the points in X. So in other words, it's just the Hermitian dot product in this vector space. But there's a, yeah, I hope that's clear. And this inner product has a nice property that the S3 action preserves this, i.e. it is unitary. So it's in U3. So these matrices are in U3 group. In other words, for any group element, the inner product is preserved. Or another way of saying it is that the matrix that we get, if I take the complex conjugate and the transpose and multiply it by pi g, I get the identity. Okay, and not only that, but the sum above, the decomposition. Obviously, if you look at the way that I defined the plane, I defined it to be the Hermitian orthogonal complement of 1, 1, 1. So this decomposition is orthogonal. It's a orthogonal direct sum of irreducible unitary representation. Irreducible unitary representations. So I'm just trying to give you like a really simple example where this theory is the way it works is kind of more transparent, easy to see. Any questions about this?
I'm guessing representations aren't always matrices, right?
1 second, let me increase my volume. I can't hear you.
Sorry, I'm guessing representations aren't always matrices, or they are.
Well, I mean, the representation is a linear operator.
Mm.
So you can choose a basis and make it into a matrix if you wish. But to define a representation of a group just means that you convert every group element into a linear operator on a vector space, and that those linear operators should compose according to the way that the group composes. And if you think about what that means, what that entails, yeah, it's like I said, it's a homomorphism into the general linear group of the vector space. That general linear group is just all isomorphisms from the vector space to itself. It's not necessarily a matrix group. Well, it's only depending on a basis. Okay.
A quick question.
Yeah.
When we're showing that the presentation, we want to show that it's a unitary. When we're writing down the inner product here, we're thinking of our operator as acting on the elements of X here, or the elements of V. So like the functions on X into the complex numbers. Which, sorry,
Yeah.
I missed that.
Yeah. So this is, what you're saying is right, that there is a slight difference between the 2 points of view that I spoke about. Like in one case, the vector space is literally generated by the elements of the finite set. So in other words, a vector consists of a formal linear combination of these elements, and then the group acting is just taking those elements and moving them. So let me clarify that a little bit. So so there's a difference. So there's 2 natural actions here of S3. For a vector of this type, let's say A E0 plus B E1 plus C E2, okay, the 1, 2, 3 cycle applied to V is going to take, sorry, I did it again, 0, 1, and 2. In my other class, I've been using the same notation, but it has to start with 0, and it's important. So yeah. Anyway, so this transformation is going to take the set. It's going to act on the set. So 1 is sent to 2, and therefore E1 is sent to E2. And so I'm going to get A E2 plus B E3 plus C E1. Okay. In this case, that's what happens. In the other case, if we think for F such that F of E1 is A and F of E2 is B and F of E3 is C. Okay, there's another way of letting it act. So let me give it a different name. Tau, let's say. Tau of 1, 2, 3 acts on F to give another function. And that function let me put it like this. The function is defined on the set 1, 2, 3, right? So the question is, what is the new function's value on the number 1? This will be, by definition, f, where you let 1, 2, 3 act on the element 1. And that's going to give f of 2. In general, 1, 2, 3, right? If the function, let me break this down a little bit more. So this is the function taking x in x to f of the group element applied to this point x, because that's going to give you another element which you can then apply the function to. So for example, this function is going to take 1 to f of 2. It's going to take 2 to f of 3, and it's going to take 3 to f of 1. So this is called, you see the similarity with dual spaces, right? So this is really what's happening, is that the functions on this set are dual. There's really a duality between these two vector spaces, even though they're both really simple. One is the dual of the other. And this is called the dual representation of the one above. So we're going to speak about this more in a little bit, so we'll get back to this later. The problem with the dual representation is that for example, if I look at tau of G1, G2, F, this will be F, acting on a point. This will be F of tau G1, G2 of X. Oh, I'm sorry, this is just the group acting on the set. And this will be F of G1, G2, X. And so this can be written as tau of G1 acting on tau of G2 on F. Excuse me. Yeah, sorry. This should be the other way around. So you see what I mean, that in this representation, the way that G1, G2, the way that a group element acts on a function is that it acts on its argument rather than acting on the vector itself. It's acting on the argument, and in this way, it's dual to the way that it was acting before. And if we look at what it satisfies, you can see that tau of G1, G2 is not equal to tau of G1, tau of G2 composed in that way. It's in the opposite way. Okay, sometimes this is called the contragradient representation for this reason, but that's really old-fashioned way of speaking. Okay, so technically this is not a representation because it's supposed to satisfy. Let me just give it the old-fashioned name. This is the contragradient. It's a name that I'm not going to use, and that's because this is not really a representation, since tau of G1, G2 is now acting on these functions. So it's a linear map, but it's not the product. It's not the composition of the two linear maps, tau of G1, tau of G2. This group, by the way, is not abelian. So rather than tau of G1, tau of G2. Does everyone see how that is? Okay, so how would you repair this? If you wanted to repair this, what could you do? If you wanted to repair these matrices so that the matrix of the product is actually equal to the product of the matrices in the correct order, what would you do in that case?
Use the inverse instead, inverse matrix.
Yeah, you could invert this. So you could say, I'm going to define pi tilde of G to be tau of G, right? Which is an operator on functions. It's acting on functions, but I'm going to invert that action. Okay, and then it is indeed true that pi tilde G1, G2 is pi tilde G1, pi tilde G2. Okay, and this thing is the thing that should be called the dual representation. Okay, and so in general, let me just, I know that I'm doing a mix of examples and theorems. I'm mixing the theory and the examples. Okay, that's just, I'm doing this because it's the fastest way to get everyone on board. But let me just give a definition. So if pi is a representation, then so is pi pi dual inverse. So this is the representation that takes a group element to first pi of G. Pi of G is a linear operator from V to V. And then we can invert it, or we could do it. It doesn't matter, the inverse or the dual. Which one is first is not important. We can dualize this. This will be a dual map from the dual of V to the dual of V, and then I will invert it so that it's going in the opposite direction, and it satisfies the representation. So this is a representation. Let me just call it pi tilde. Pi tilde is now from G to GL V dual. So that's really what's going on. Okay, so so we started discussing irreducible representations, right? And remember that the definition is that V pi is an irrep of G when there does not exist a proper non-zero invariant subspace. And maybe a nice feature, just a remark, a nice feature of unitary representations. So these are representations which preserve the Hermitian inner product, is that if U inside V is invariant, then the orthogonal complement of U is also invariant. So as soon as you find an irreducible, as soon as you find an invariant subspace, which is sent to itself by G, then its orthogonal complement will also be sent to itself by G. Okay, so you're really trying to look for invariant subspaces. As soon as you find one, you can split it off from the vector space by just forming its orthogonal complement and then expressing the vector space as a sum of those two subspaces. And then you can give one subspace to your friend and let them decompose that one, and then you can work on the remaining one. And then every time that you find an invariant subspace, you can just, send it off to the parallel processor and decompose further until you get something that's irreducible. Okay, so here's our first kind of non-trivial theorem in representation theory. So this is called Schwer's theorem. Okay. If a complex representation, complex just means that the vector space is a complex vector space. If a complex representation V pi is irreducible, then the only linear maps M commuting with all pi G are multiples of the identity. So complex representation, irreducible. So you should think that we have a group. It's acting on this vector space. Okay, so you have a whole bunch of matrices which are acting, and they satisfy these nice conditions. They form a group. Those matrices form a group. They're all invertible. And think of it as a symmetry of your space. And so then you're interested in whether there might be any linear transformation which is compatible with that symmetry, meaning that if you apply that linear transformation before or after doing a symmetry, you're going to obtain the same result. In other words, if you apply this transformation and then move it using a symmetry, that would be the same thing as moving the original point by the symmetry and applying the transformation. And somehow the point is that the matrices, because the representation is irreducible, right? You should think that what that means is that when you pick a vector, right, that vector, when you act by all the matrices in the group, it's going to be moved around, right? And it will kind of sweep out the entire vector space, or at least it will sweep out a bunch of vectors that will span the space, right? Because if you took a vector and you hit it with all the matrices and it stayed within a small subspace, then that would tell you that that subspace is going to be a sub-representation, or it will be an invariant subspace. So the point is that the matrices are they're really moving things around a lot, and so it prevents the possibility for any other matrix to commute with it. That's basically what's happening. So here's the proof, a pretty simple proof. So any such M would have an eigenvalue. because we're over the complex numbers. So let V lambda be this eigenspace. So this is a non-zero subspace. Okay, but now the problem is that this subspace is determined by M, right? But everything in G, all of the matrices in the representation, they're assumed to commute with M. So, for example, if we if V is in V lambda, if it's an eigenvector for lambda, then pi of G V is an eigenvector itself. So this means that V lambda is an invariant subspace. So that would contradict irreducibility unless it was the whole thing. Unless V lambda is all of V, in which case M is just lambda times the identity. Okay, so it's really just the idea that an irreducible representation is really moving the vector space around, a lot, and it prevents any other vector and any other transformation from commuting with it. Okay, so this is a pretty innocent-looking theorem, but it's incredibly useful throughout all representation theory. It's basically just telling you something important about the structure of irreducible representations. Let me show you some corollaries of this. So let's say that G is abelian. So if G is abelian, meaning that G1, G2 equals G2, G1 for all G1, G2, so it's a commutative group, right? Then what does that mean? Well, this implies by the property of representations that pi of G1, pi of G2 is equal to pi of G2, pi of G1 for all G1, G2. So if the group commutes, then the matrices that represent those group elements must commute. And therefore, we've got a whole bunch of matrices that commute with all of the pi g. Namely, each one of the pi g's is a matrix that commutes with all the other pi g's. So this means that each pi g satisfies m pi, satisfies the conditions of the theorem. So this means that pi of g, this means that if V is irreducible, then then pi of G is equal to some lambda G times the identity for all G. It acts by a scalar. All of the group elements act by scalar. And that means that another way of saying it is that, so this means that in a very strong sense, everything is simultaneously diagonalizable in any basis, right? I mean, any basis, all of these things are just scalar multiplications. In any basis, each one of these pi G just looks like, a number, some number times the identity matrix. So what does that mean? Well, that's not irreducible, because I can just take a direct sum along the diagonal. So so this tells us that the only irreducible representations, so the only irreps of G abelian, complex irreps, are one-dimensional. So any abelian group has only one-dimensional complex representations. Okay, so let me give an example of such a thing. Suppose that we took let's take Z mod NZ to be our group. This is an abelian group. It's an abelian group, and I want to define a representation. So for every group element, I want to define a matrix. I want it to be an irreducible representation, so that's going to be a 1-by-1 matrix. Okay, so this group has a generator. Let's construct an irrep of Z mod NZ. So this Z mod NZ has a generator. Let's take 1 to be the generator. The identity, this is the identity. So the identity certainly has to be sent to the 1-by-1 matrix. Oh, sorry, bad notation. I don't know what you're used to using as notation for Z mod NZ, but let me just use an underline. So we have 0, which is the identity, the additive identity, and 1, which is the generator. And then the point is that this should be sent to the identity matrix, which is just a 1-by-1 matrix with 1 in it. 1 is the generator. It must be sent to some 1-by-1 matrix. Omega is a complex number. It has to be invertible. So it's a non-zero complex number. And what must it satisfy? Well, being a generator, the relation for this group is that if I add 1 to itself n times, I get the identity. So that means that omega, the matrix omega raised to the nth power, should be the identity matrix. Or in other words, omega to the n is equal to 1. So it has to be an nth root of unity. So the matrices are exactly these complex numbers. Okay, and it's just a one-dimensional representation over the complex numbers. And this is a good example. Now you could have, if you choose omega to be just 1, that is an nth root of unity, right? Then what you'll get is a representation where all the matrices are just 1. And that's called the trivial representation, when you send every group element just to the unit. And then when you take omega to be a primitive nth root of unity, that gives another a non-isomorphic representation, right? You cannot expect to change basis to make the non-trivial representation look like the trivial one. So these two are different representations of the same group on the same dimension vector space. Okay. Okay, so next theorem. Okay. I'm going to classify the representations of U1. But before I do that, I just want to keep, open it to questions. About representations so far. Nothing? Clear? Okay, let's classify the representations of U1. So irreducible representations of U1. Okay, so I'm going to, so here's the theorem. The theorem is that all irreducible representations of U1, and these are the complex ones, all the irreducible complex representations of U1 are given by an integer, k. This integer tells you which power to raise this to. For k in Z, called the weight of the representation. Okay, so let me give a short proof of this. Okay, so first of all, let me just break it down as a series of points. So the first point is that U1 is abelian. So this means that the dimension of the vector space is 1. So this means that the representation is really mapping U1 into C star, the non-zero complex numbers. And this should be a homomorphism, a group hom. So what we're really doing is we're classifying group homs from U1 to C star. Okay, now, so let me draw a diagram. So there's going to be U1 here, the circle. There's going to be the representation to C star. And then I'm going to do what we normally do when I just did it here. Notice I did something that's kind of innocent little thing where I represented the element of U1 as the exponentiation of a real or purely imaginary number, right? So really what I'm doing there is I'm noticing that there's an exponential map from R, which you could call it e to the ix, let's say, or e to the I theta. Okay, and that's a group homomorphism. And so And so if I'm trying to look for a group homomorphism from U1 to C star, well, I know that if I have one, then I could compose it with this exponentiation, and I'll get a group representation of R. So if I compose these two, I'll call this F. So this defines F. And F, so by the representation definition, we know that F of theta 1 plus theta 2 is going to be the product of F of theta 1 and F of theta 2. So we define F to be pi. We define F of theta to be pi of e to the I theta. Okay, so we're just being a little bit pedantic about the way that we describe the circle, but bear with me. So, oops. Okay, and so there's a little bit. So I'm going to use something now, which I'm going to gloss over a little bit, and that is that these representations, they're smooth. So meaning that, this U1, it has a parameter. It has a coordinate theta, local parameter theta, and this C star has a local parameter Z, let's say. And if we look at this map pi, okay, it's differentiable. These representations are differentiable. Now, there's two ways to go. One way to deal with this problem is that I could have said that we're going to classify smooth representations only. We're just going to impose the fact that the representations as maps, that they're differentiable. But people don't usually do that because of the fact that these groups have a lot of automatic smoothness. They're automatically smooth in a sense because of the way that their multiplication is defined. And this is it's a little bit of a complicated topic, which I don't want to get into. But the point is that this map F is a smooth map, and so is pi, and all of the maps here that I'm drawing are always smooth. So we can differentiate this. It's an interesting exercise to try to avoid this and try to prove it from first principles, but I'm going to not do that. So so if we differentiate this, so the way I'm thinking, this is the way I'm thinking. I have an idea of what the answer looks like, and you see that if I believe that the answer is like this, that these are all the representations, right? Then how am I going to distinguish one from another? An easy way to do it would be to differentiate this with respect to theta. And then the k is just going to come right out in front. So that's my strategy. I'm going to argue that if we differentiate this thing, then there's got to be an integer showing up in front. That's the strategy. So if we differentiate with respect to theta 1 at theta 1 equals 0, what am I going to get? Well, I'm going to get f prime at theta 2 is equal to f prime at 0 times f of theta 2 plus f at 0 times, well, f of theta 2 doesn't have any derivative with respect to theta 1, so that's just 0. Okay, and so this is a constant multiplied by f of theta 2. So this is a differential equation for f. F prime is a constant times f. So we can solve this. And it's that f of theta is a constant times e to the c theta. Okay, so now we just need to check. So now we need to check what is needed for pi to be well defined representation. Okay, so the first comment, let me just see, I kind of traveled here. Let me do it this way. So first of all, we know that at 0, this thing has to be, 0 is sent to the identity element of U1, and pi must send that to the unit in C star. So this must be equal to 1, and this tells me that k is 1. So that deals with k. And the other question is, what is C, right? And this is where this comes in. So in order for f to factor through this projection, this exponential map, right? We need that, for example, f of 2 pi, this is going to be e to the I 2 pi, pi of this. But e to the I 2 pi, this is just 1, and I know that is equal to 1 as well. Okay, so this this is telling us that e to the c times 2 pi must be equal to 1. And this tells us that c must be I times an integer. So you see, like the condition, you could think that as you increase the angle, right, you're solving this differential equation and you're getting this kind of exponential behavior. And as soon as you get around the circle, there's a condition that the value of that function must be equal to 1 again. And so the number of times that it rotates around as you go around the circle, it must be so that there's an integer number of rotations of the complex number as you move around, so that when you get back home, the complex number is equal to the unit 1, is equal to the number 1. So in conclusion, we get that f of theta is, which is that pi of theta is e to the I, or sorry, let me just say that's it. That's the proof of the result. Yeah, Thomas.
Oh, this is just, sorry, so maybe a silly thing, but
No.
when we're dealing with angles, if we
Yeah.
could use a different, like a pi with like a hat or something, or like a tilde for the representation, it would make things clearer. Because it's like, for a second there, I was really confused because I thought we were on number 2 there. I thought we were multiplying by pi for a minute. No, it's just like, wait, what?
It's true. Yeah, you're right. Yeah, I don't think this is going to happen anytime in the future, but it's a good point. Okay, so we've got all of our representations of our irreducible representations of the circle. Okay, let me take a 10-minute break. We'll be back at well, actually, let's go to 3:25. I'll be back at 3:25. Okay, can I restart? I think people are still offline. Okay, good. So if we have all the irreducible representations, so this means that any, so this means that a general representation of U1 may be written as follows. Into these. And so that means that if we have, so if U1 let me be a little bit more precise in this statement. It's not a theorem or anything, but I just want to make sure that, so a general unitary representation of U1, okay, if someone gives you a unitary representation of U1, right, what you should do is you should look for an invariant subspace that's going to be a one-dimensional subspace. You could easily find that just by picking a vector and looking at how the U1 action spins it around, and that will give you a one-dimensional subspace. And then take its orthogonal complement, and then look at that orthogonal complement and just iterate that process. But based on this, we see that a general unitary can be decomposed into these. So if U1, if we have a representation into let's say H, or it's not, let's say V, a complex vector space, then this V, I can decompose it as, I'm just going to use slightly different notation just to emphasize a point. Q1 plus V Q2 plus V Qn for integers Q1 up to Qn. And then I suppose there could be repetitions here. There's no reason for them to be distinct. And then pi of theta, this would look like this would look like the exponential of I q theta, where Q is a matrix of integers down the diagonal. Okay, so the representation pi of theta has been diagonalized. It's I mean, in this case, it's diagonal just because of the fact that the irreducible representations have dimension 1. And this is just the generalization of the form that we just saw. C was equal to ik, and so we got representation of the form e to the ik theta. The point is that for a larger vector space, that k becomes a matrix, a diagonal matrix of weights. These are the weights of the actions, of the action. And these weights, that's what we call it in mathematics. In physics, it has a different name. These integers in physics are called what? If anyone wants to hazard a guess. They're called, anyone?
Quantum numbers?
Charge.
Charge.
You've heard of charge, right? Electron has -1 charge. Neutron has 0 charge. That's literally what it means. This is the matrix of charges. And this is the charge operator. Notice that it's self-adjoint, which means that it's an observable. As we talk about it all the time, the charge, it's observable. We see that this Hermitian, this self-adjoint is being converted into a skew adjoint by the multiplication by I. Therefore, we're exponentiating a skew adjoint matrix, and we're getting something in the unitary group, just as we discussed. So the idea is that you could think just very roughly speaking, you could think that the big representation is some kind of a particle, which is made, or like a conglomeration, an agglomeration of particles, something like what you find in a molecule or atom, and that there's a group that's acting on it, the U1 group. And well, this is a little bit more difficult to explain. This U1 group is not a rotation group in space. It's not a rotation in space, but rather it's a rotation in some kind of internal state space that the particles have. It's like a little circle that every particle has on top of it in its mind. Okay, and the particle, well, not really. You could kind of think, yeah, it's like an internal space, and the particle is on that circle, somewhere on that circle, and you can send a signal to the particle, and you can say, okay, move, just rotate in your internal space, rotate by 10 degrees. You can send it a signal, rotate by 10 degrees inside your internal space. And that particle will do the job. It will rotate in its internal space. Okay, but which direction and how fast is dictated by its charge. In other words, it's dictated by which irreducible representation is that particle operating under. Okay, and that signal is known as light. Okay, you send a packet of light, the light hits the particle, and what the light does is it rotates the particle inside its internal angular space. Okay, and but the light doesn't know what the charge of the particle is, right? It's only the particle that will know whether it's going to move one way or another way inside this internal space. It's amazing how many people I've explained this to actually believe that I was not telling the truth, that I was somehow making it up, but it's not, but I'm not. Okay. So that's the that's the decomposition of unitary representations of U1. So the reason why this, by the way, the reason why this U1 thing is so important, the representations of U1, is because when we need to study the representations of any other group, as we're going to do either later today or next week, we're going to study SU2. What we're going to do is we're going to look inside SU2 for a U1 subgroup, and then we're going to use that U1 subgroup to classify the representations, to help us classify the representations. So the U1 case is really the most important case in representation theory. And the next important case is SU2. And once you understand those two, you can pretty much understand the basics of representation theory at large.
And like finding these U1 subgroups, is that only going to be guaranteed because we're considering Lie groups? not like in general other groups?
Yeah, that's right. Yeah. I mean, these groups that we're focusing on are things like U1 and SU2 and SU3 and things like this, which are Lie groups. In the case where you have finite groups, then there's something similar that happens. I remember I did the Z mod NZ. This is like the finite group version of a circle. And so you will do a similar thing. You'll look for one-dimensional subgroups that will be helpful. Yeah, there's a whole, when you learn representation theory, usually actually they focus more on the Lie group case, but they should do a little bit on finite groups as well. Those are the two main cases. Okay, so we're going to talk about SU2, but I'm going to do it next week, and instead, what I'll do now is introduce the.
Oh, sorry. I guess I'll ask. As a graduate student, like are we having class during reading week or no? Because I think for graduate students, like it's optional.
No, there won't be class next week.
Okay.
That's a good point also. So for that reason, I'll just do something that has a good endpoint. I got screwed up last class. The last Friday was a disaster from all my planning. So let me just find. Okay, yeah, got it. Okay, simplest quantum system after the qubit. A free particle on the circle. So we have a circle. That is the space. That's the configuration space. And we've got a point on there. And so the classical system has phase space Okay. So in the classical system, we just have a phase space, which is the cotangent bundle of S1. So we have, it looks basically like a cylinder. And because it's free, that means there's no forces acting on it, which means that the only term in the Hamiltonian will be the kinetic energy. And the kinetic energy will just be like 1/2 p squared, where p is the coordinate along the cylinder. That's just the squared norm of the momentum. So when we allow it to evolve under this Hamiltonian, right, it's going to we would need to find the vector field corresponding to this if you apply dh, and I mean if you look at the vector field which comes from this, you'll get p d by dx, and the flow will look like this. So there's going to be a vector field that has a constant horizontal velocity, which moves the circle, moves the particle around the circle at a particular speed. But if you increase the value of the momentum, the velocity vectors get larger, right? And there's zero at zero momentum. And then on the other side, they move in the other direction. So what I'm drawing is the vector field, the Hamiltonian vector field. Okay, and the trajectory of the particle can look like this. If the particle is stationary, it can just remain there for all time. Or if it is here, if you give it a little bit of a push, then it will start moving along the circle at a constant speed, constant angular speed. But if you give it more of a push, then it will go at a constant speed, but which is faster. Okay, so all of this is like somewhat immediate. Once you say, okay, the phase space is just a cylinder and the Hamiltonian is just the norm squared of the vertical coordinate. So what does this mean? This means that the energy h of a trajectory or solution, the energy of a solution, is of course constant. And so it's sorry, the energy of a solution is constant, but also it can be any real number. Because I can decide to give that particle any push I want. Okay, and so the spectrum of the observable h is anything in the real line. It can be anything in the real line. Okay, and so that's pretty much if this classical system, let's say this classical system was really, really small and it was it was let's say you reward in a pendant on your neck, this little circle with a particle on it, and it was really like microscopic or something, and then you wanted to use it in order to cool down your very hot fingertips or something, and you wanted to just shed some energy into this system and use it as a heat sink, right? So if you had a certain number of units of energy, if you had a certain amount of energy, and you just grabbed onto that little circle, you would transfer all that energy could go into the circle, and it would start spinning at some random angular speed, and it would absorb that energy. Okay, so there's no constraint. It's not like the energy that you have has to be a certain energy in order for the circle to absorb it. The circle could have any energy at all. Now let's do the quantum version. Okay, so in the quantum version, the vector space, the complex vector space, we're going to take to be the functions on S1 with complex values. Now, what kind of functions should we take? Well, for now, let's just use C infinity functions, so smooth functions. What we're about to do is introduce an inner product. And then we're going to complete this vector space using the inner product. And it's going to become a Hilbert space, which is called L2. So the completion is called L2 of S1 with complex coefficients. But this is not important for what I'm talking about today. This inner product, if I take two functions on the circle and I want to evaluate, if I want to take their inner product, right, I have to get a number. So whenever you have functions like this and there's some operation which outputs a number, there's only a few things that it could usually be. It could either be that it's an evaluation of the function at a point, which here I can't really do because there's no special point, or it's an integral of the function over the whole space, which gives you an average value, right? And that's exactly what this is. So this will be the integral of f bar times g d theta, g theta, d theta. Okay, so it's exactly the analog. So it's the exact analog of the sum of f of p bar g of p, where p was an x. If you remember, that was the inner product that we used in the finite set case. Okay, and so these functions, they're called wave functions. And they have this inner product. So right. Okay, now, in order to make a quantum system, so this is the vector space with the inner product, but if I want to make a quantum system, I need the Hamiltonian. The Hamiltonian will dictate how this thing evolves in time. Now, in order to get the Hamiltonian, I need a self-adjoint operator. Now, I could just define a self-adjoint operator. There's plenty of them. But as is always done in physics, I want to get this self-adjoint operator from a reasonable source, or I want to focus on the good ones, like the ones that are really transparent and that are present here due to the fact that we have symmetries, right? Anytime that you have a symmetry, the symmetry is generated by a skew adjoint transformation in the Lie algebra. And that, if I multiply by I, becomes self-adjoint and gives me an observable, which I could use to make the Hamiltonian. After all, the Hamiltonian is supposed to give me the evolution, the unitary evolution in time, right? So it's natural to look for symmetries that could be used to define the Hamiltonian. So what symmetries do we have? So we're looking for self-adjoint operators. Hopefully one which plays the role of this kinetic energy. So we want sorry about that. So we're hoping to find one that looks something like the energy and that it will play the same role as that. Okay, so I'm going to look for symmetries of this space. Now, this is why I was explaining the finite set, that if you have a group that's acting on the finite set, it will also act on the functions on that finite set. Well, here, this is not a finite set. It's all of S1, all the points in S1. And I'm looking at the functions on S1. Now, S1 has an obvious group of symmetries, namely the rotations. Of S1. So, for example, if I'll use phi I'll just not to be confusing, I'll call S1 X, that's the space, and I'll call S1 the group, just S1. So we have an action of S1 on X, which takes theta and a point X to phi theta of X, which is, actually I'll use Z for a coordinate on the circle, for a point on the circle, and this will be e to the I theta Z, just rotation. Okay, and if we look at how this, so this, the fact that phi acts on X means that I'm going to have a dual action on the functions on X. So let's say that f is now a function on S1. Then what I claim is that I can naturally act on this function to get another one, right, whose value at Z is exactly by definition is the value of the function, but at a shifted argument. So this phi theta star, this shifts, this acts on functions by argument shift. Plus theta. So it will act on your function to give you a new function whose value at a point is the value of the old function at a shifted point. Okay, and in the example that I was doing before, I needed to invert this thing in order to get an action because it was the dual representation. In this case, I don't actually have to do it because it's an abelian group. So I'm just going to leave it as this. So now the key point is that this action of S1 on V is unitary. Why? Because if I integrate phi theta star F bar phi theta star G d theta, right? All I'm doing is I'm shifting the argument of both of the functions, right? So it's really just an integral over S1 of F. Let me see, a dummy variable. I need a dummy variable. Let me call it theta tilde. So this will be F of theta tilde plus theta G bar, G of theta tilde plus theta d theta tilde, right? And this is the same thing just by doing a change of variable as F of theta tilde bar G of theta tilde d theta tilde, because theta is constant in this integral. So this is telling me that phi theta star is equal to this. So we've got a unitary transformation. Okay, so translation or rotation in the space is generating a unitary transformation of the vector space. That's the cool thing. Okay, and Okay, and that's helpful because I can now use this representation on the vector space. Now I have U1 acting on the vector space, right? And I can differentiate that to get a Lie algebra element that is acting on the vector space. So if phi theta is a unitary operator on V, then d by d, and by the way, at theta is equal to 0, it's equal to the identity. Right? Then what I can do is take the derivative d by d theta of this operator at theta is equal to 0, and this will be a skew adjoint operator. And what is this? Well, so this operator, if you think about what this is, your operator is basically shifting the argument of f, right? So it's like f theta, let's say theta plus t is the operator. Let's say phi t star f of theta is equal to this, right? So if I try to differentiate this, what I'm going to be doing is doing f theta plus t minus f theta divided by t. If I differentiate this operator of shifting the argument, that's literally the name, that's exactly how we define the derivative usually. So this skew adjoint transformation is exactly the operator d by d theta on functions on S1. And indeed, if you, there's a famous result, which you all know, that if we take d by d theta of f g d theta, and if I do then this is equal to 0. This is something you probably call integration by parts. F prime g integral is equal to minus g prime f integral, right? So this means that it's skew adjoint. If this is skew adjoint, so this operator d by d theta is skew adjoint, and therefore minus I d by d theta will be self-adjoint. So here we have our first observable. Okay, and it turns out that this observable is exactly the observable that we want, because this one is the analog of the momentum observable. Okay, and so the analog of p squared over 2 is going to be the square of this operator. And the square of this operator is going to be minus 1/2 d squared theta, d squared by d squared theta. It's the second derivative. And this is known as the Laplacian operator on the circle. So I know that I've run out of time, but the point is that just by looking at the symmetry, which, by the way, the motion along that circle, right? In classical mechanics, it's exactly it's exactly the observable P is the one that generates the Hamiltonian vector field d by dx, right? So or in this case, d by d theta, right? So the function P, which occurs in the Hamiltonian, P squared, that function P, it generates a certain Hamiltonian vector field which rotates the configuration space. Okay, and so the momentum is the generator of that symmetry. And if we now look at the wave functions, and we just do the same thing, but we ask the question about wave functions, we say, okay, we have this symmetry, it acts on wave functions as well. And now let's look at the self-adjoint operator corresponding to that symmetry. That's what we should call the quantum momentum. And indeed, if we call this the quantum momentum, P hat, okay, this observable can be squared, and I get another you get another self-adjoint operator. So this is also self-adjoint. And it's the quantization of energy. Okay, so that means that now what we have to do, and we don't have time to do it right now, is to solve what are the possible eigenstates of this operator, this energy operator, on the functions on the circle. What are the possible eigenstates? Because those would be considered those would be the possible measurements of energy. And the thing that you all know is that finding eigenspaces of the Laplacian, it's like f double prime is equal to c times f. And you know the solutions to this. They're waves. Okay, and those waves are now defined not on the real line, but they're defined on the circle. Theta is periodic. So that means that the wavelength must be an integer fraction of the circle's circumference in order to be a solution. This eigenvalue tells you the wavelength. So the point is that because it has to fit on the circle, because this wave has to fit on the circle, right? That means that the wavelength can only be a certain discrete set of numbers. And therefore the eigenvalues of the energy can only be a discrete set of numbers. And here we see the main difference between the quantum and the classical system. The main difference, which is of such high importance, is that you cannot expect to be able to dump energy into this system however much energy you want. The system will only eat a very particular eigenvalue, and their discrete set of these eigenvalues. And if you provide some amount of energy, a quantum of energy, which is not of that right size, it won't go in. It can't go in. So this system, this one's a really, this one's it's a really important quantum system to learn first, I would say, even before the harmonic oscillator, because the harmonic oscillator is a particle, it's basically the spring. It's a particle acting under a force. Here you don't have that. It's just kinematics. It's just a particle that's moving around on the circle. And the point is that it's due to the shape of the space, you're not allowed to have certain energies. It's kind of incredible. You cannot put a certain, that system cannot contain certain energies. Okay, I'll leave it there. Have a good reading week. Enjoy the assignment. The assignment's a little bit longer, but so just be careful not to start too late. Most of it is just reading what's in the assignment and learning the material. Any questions?
I have a quick question.
Yeah.
Just so we're considering C infinity on the circle. Is that because, like we did with the switch, we basically take the free vector space on the positions in the non-quantum system? Then for every point, we get a dimension.
Yeah, correct. Yeah. The functions on the configuration space is the most typical way of building the Hilbert space. This works in a very large, very wide variety of systems. Sometimes you need to do something more fancy, and that's why they invented a geometric quantization.
A point in this space really represents like a distribution over this.
Sorry, a point in which space?
A point in C infinity S1, because then
don't answer your question before you ask it. What are you wondering about?
What does a point in this space correspond to? If it's just a
point, what do you mean by a point?
Well,
a vector in this vector space.
Yeah.
Well, you tell me. What is this vector space? This vector space is the vector space of the quantum system. Yes.
Yeah.
So what is a vector in the vector space?
A function on S1. So
no, I mean, I just mean the interpretation in quantum mechanics for this vector is what?
The state of the system.
Yeah, as long as it's non-zero, right? Yeah. And you can take a constant scalar multiple of it. That ray or a line inside this space, the constant multiples of a single function, that wave function, is a state in the quantum system. Okay, and what's the interpretation? Well, okay, I mean, it depends what you want to know. Like if you want to know a certain observable, then you measure that observable, and that will project that vector onto the eigenspaces of the observable that you're interested in, with certain probabilities, which depend upon the position of that vector. So that the position of that vector relative to the eigenspaces of the observable that you're interested in is what determines the distribution, the probability distribution on the spectrum, which tells you what the relative probabilities of measuring that observable, being whatever values it can have.
Okay.
So it's the interpretation is no different than it was for the switch. It's no different. I tried to develop the sequence so that the idiotic examples at the beginning actually contain all of the concepts. So, if you dismiss those as being too simple, then, well.
Thank you.
You're welcome. As you're going to see, the problem, the problem that you often encounter in quantum mechanics is that, why was I able to obtain this quantum system? Why? The reason was very simple. I just took functions on the classical space, configuration space, and then I used the symmetry of the classical space, and I basically tried to cook up a quantum system that had that same symmetry. And so that was possible. But in general, it is not possible to take a given quantum system, a single one of them, and obtain it's usually not possible to take a quantum system, a classical system, and produce a unique quantum system. You can probably produce a whole bunch of them that limit to that classical system. So the classical system, you should kind of think of it, the way I like to think of it is that you have all these quantum systems. It's like a huge, huge space of different possible quantum systems. But at infinity, in the limit, in the completion of the quantum systems, you have the classical systems. The classical systems are like the celestial sphere. They're very, very far away. You can try to get there, but you really would need a sequence of quantum systems, which is somehow limiting to the classical system. And things like geometric quantization, they are basically trying to bootstrap their way from the classical system into the quantum bulk, but they always require extra pieces of information in order to be able to do that. And and it's just not it's not a general framework, and it's not enough of a general framework. Okay. Anything else? Oh, I see. Romain asked this question in the chat. I see. Oh, and someone else said, I prefer to just believe the whole real world is made of mathematical objects and structures.
I think that's when you were saying something about people struggling to buy what you're telling them about how
Oh, right, right.
Math stuff relates to the physical world.
Yeah. Yeah, I wonder what that really means to for the real world to be made of mathematical objects. That's an interesting idea.
Ask Max Tegmark. He apparently knows.
Yeah. Well, I don't know. I doubt it. Yeah, there's definitely. Yeah, perhaps in 10 years I'll be teaching a course about pre-quantum mechanics in which we discuss that crazy theory of Wolfram's, where he now claims to have a way to derive all of the quantum laws, as well as GR, as well as the emergence of space, as well as everything. If there's anything, by the way, if there's anything that you guys like, if there's any major problems in life that you have, you should just tell him, because he could solve everything. It's all in there, everything. I would like to understand that a little bit better. It's just that the way that he presents it is, as always with him, it's kind of a little bit of a crazy presentation. But if anyone here has studied that or wants to study it, I would be, that would be a good USRA thing to do. I think that would be great. I would love to have an undergraduate summer research person to investigate the Wolfram theory, and we can try to see if it has any merit.
See if he's actually saying anything.
Yeah, no, it looks interesting. I mean, he's honestly speaking, if there was to be a replacement for fundamental physics, he would be a good candidate for a human being to actually come up with it, due to his history, due to, like, I know about his academic history and what he did, and the type of things he worked on, and it makes a lot of sense, especially if you believe, like Thomas does,
stuff.
that the universe is just a computation.
Complex emergence, all that weird stuff that happens.
So did you study this thing that he's been
I haven't actually taken a look at that. No, I'm curious now, though.
Maybe you should.
I'm gonna take a look at this.
You know, while you're learning quantum mechanics, why not learn this other thing early? You know,
have some fun.
Are there any like good resources to?
Oh yeah, he has an
learn a little
entire
bit about
website devoted to teaching people it. If you go to the Wolfram, it's all with his name. Everything has a TM, copyright Wolfram. I'm surprised that you don't have to pay for every page that you reload. It's oh my goodness, this is all being recorded. Okay.